This is FRQ 2026 question of kinematics. Uh, Two small disks R and S are on straight horizontal tracks. So these are two disks R and S which are placed over horizontal track, which is of course frictionless. So you don't have to worry about frictional forces. At t is equal to 0, disk R of mass m0 is located at position x is equal to x0. So I am assuming that at t is equal to 0, its x coordinate is 0. Disk R is initially moving with speed v0 in plus x direction, and disk S of mass 3m0 is initially at rest. So this disk R was moving with velocity v0, and this disk of mass 3m0 it was at rest. So at t is equal to t1, disk collides. So obviously there will be collision between them. So after collision, Uh, this m naught, that is disk R, was found to be moving with velocity v naught by 2 in minus x direction. So this is moving in this direction, which is v naught by 2, and this 3 m naught, let us assume that it is moving with velocity v towards right. Now, part A, momentum vector diagram of disk R and disk S before collision is shown here. So this disk S was at rest, so its momentum is 0. And this disk was moving towards right. Its momentum has been represented by this arrow. So what was momentum of this disk? It was m naught into v naught. So this m naught into v naught has been represented by this arrow. So how many units? 1, 2, 3, 4. So total 4 units are there. So 4 units has been used to represent momentum m naught v naught. So after collision, this 3 m naught would be moving with velocity v, and this m naught would be moving with velocity v naught by 2. Now, we have to represent momentum of disk R and disk S after collision. So, as I've already told you, that m naught v naught, which is momentum of this disk, is represented by 4 units. And what is momentum of disk R after collision? It is m naught into v naught by 2. So m naught into v naught by 2. And what is m naught v naught? It is 4 units. So m naught v naught is 4 units divided by 2. It comes out to be 2 units. So m naught v naught by 2 should be represented by 2 units and of course towards left. So please see here, we have represented it by 2 units. So this is momentum of this R. For or in order to find momentum of disk S, I have used principle of conservation of momentum, and you have to mention it because there is no external force. So in the absence of external force, I am saying there is no external force. External force is 0. So I can say momentum of system is conserved. So momentum of system is conserved. That is, momentum before collision should be equal to momentum after collision. And I am talking about system which consists of this disk R and disk S. So what was initial momentum of system before collision? It was 1, 2, 3, 4. 4 units towards right. So after collision also, momentum of the system should be 4 units towards right. Now please see here. 2 unit has been mentioned here, or 2 units is momentum towards left, and net momentum should be 4 units towards right. So I can say net momentum, or I can say that momentum of this disk will be 6 unit towards right. So 6 unit minus 2 unit. Of course, answer will be 4 unit towards right. So as per momentum conservation, I haven't solved velocity of this uh, disk, but of course I can say that initial momentum was 4 unit. So afterwards also momentum was 4 should be. I can say that since initial momentum is 4 units towards right, so final momentum of system should also be 4 unit towards right? But we do have 2 units momentum of r towards left. So we should have 6 unit momentum of this s towards right. So this is 6, this is 2. So 6 minus 2, that should be equal to 4. So this 4 and this 4, I can say momentum is conserved. Now, let's see part B. So they are saying, starting with conservation of linear momentum. I have already told you that we can apply momentum conservation because there is no external force acting on our system. Derive expression of kinetic energy of disk S immediately after collision. Okay, so after collision, I have to find velocity v with which this 3m mass or 3m naught mass is moving. So as per momentum conservation, I have told you why we are applying momentum conservation. In order to get all points, you should mention that collision, there is no external force, therefore momentum should be conserved. And further, you should know that momentum is a vector quantity and it should be accompanied by proper sign, right? So this is our system. What is initial momentum? M naught V naught, and this was at rest, so it should be 0. This M naught was moving with velocity minus V naught by 2. So this M minus V naught by 2. So here we have incorporated negative sign. Plus this 3m naught was moving with velocity v. So solving this, I get v is equal to v naught by 2. That means this 3m naught mass was found to be moving with velocity v naught by 2 towards right. So now, what is kinetic energy of this disk? It should be equal to half. Its mass is 3m naught and its velocity is v naught by 2. So this is half mv square. This is its kinetic energy, which comes out to be 3 by 8 m naught v naught square. So now let's see part C. In this part, a graph of position of m naught, that is x coordinate of m naught and x coordinate of 3m naught, is plotted as a function of time. So we do know that collision take place at time t is equal to t1. So initially, this m naught, its x coordinate was given to be 0. So 0 comma 0, let it be the coordinate of this m naught at t is equal to 0. And in time t1, distance traveled by this m naught, which is moving with velocity v naught, will be equal to v naught t1. So what will be x coordinate of 3 m naught mass? That will be equal to v naught t1. And I'm saying let y coordinate be equal to 0. So at t is equal to 0, x coordinate of m naught was 0. So this is time t. At t is equal to 0, x coordinate of disk r was 0. At the same time, this 3m naught, x coordinate was given to be v naught t1. So this 3m naught is nothing but disk s. So this is disk s. At time t is equal to 0, its x coordinate was v naught t1 as indicated here. Now, x coordinate of this m naught or disk r is changing since it is moving with velocity v naught. So you can see here, disk r, as time is increasing, its x coordinate is changing. But at the same time, since this 3m naught, which is disk s, is at rest, its x coordinate is constant. So it is not moving, while this disk r is moving with velocity v naught. So after collision, when collision take place? Collision take place at time t1. So at time t1, collision take place. And after this, disk S also starts moving, and hence we can say its x coordinate will change. So you have to mention that net external force on m naught and 3m naught is 0. Of course, normal reaction will be equal to mg, so external force is acting, but net external force is 0. Whatever force is exerted by m naught on 3m naught, it can be considered as internal force. At the same time, this 3m naught will be exerting force on this m naught. So they are internal forces. So in the absence of external force, I can say that momentum of system will not change and velocity of center of mass will not change. And therefore, I am extending this line because velocity of center of mass is constant. Because for straight line, slope is constant. In here, slope is nothing but velocity. By applying momentum conservation, we found that 3m naught was moving with velocity v naught by 2. So, what is distance traveled by this 3m naught, which was moving with velocity v naught by 2 in time t1? So, velocity is v naught by 2 and time is t1. So, v naught t1 by 2 is distance traveled by this 3m naught, which is nothing but this s. Now, see here, v naught t1 has been given to be 1, 2, 3, 4, 4 units. So, v naught T1 is 4 units. So 4 divided by 2 comes out to be 2 units. So distance traveled by this 3 m naught will be represented by 2 units. So kindly see, this is the disk S, and distance traveled by this disk in time T1 is nothing but 2 units. So this is graph xt graph for disk S. Now this m naught was moving with velocity v naught by 2, but towards minus x direction. So velocity is v naught by 2, time is t1. So I can again say v naught t1 by 2 is nothing but 2 units. But since it is moving towards minus x direction, its x coordinate should decrease. So we are decreasing x coordinate by 2 units. So now this is graph for your disk. So this is graph for disk S, this is for disk R, and this is for center of mass. So now let us see part D, in which it is said that magnitude of change in momentum of disk R and disk S is given by or represented by these two expressions. We have to find the relation between change in momentum of S and change in momentum of R. So the fundamental concept once again here is, since there is no external force, we can say momentum of our system is constant. So you have to mention this, there is no external force. Momentum of system is constant, then it implies change in momentum of system will be zero. So change in momentum of system, that is delta PR plus delta PS, should be equal to 0. So from here I can say delta PR is equal to minus delta PS. Of course, you can apply, since it is vector quantity, you can apply vector notation here as well. So of course, change in momentum of R will be equal to change in momentum of S.